On September 18th, 2001, with the United States still reeling from the September 11th attacks, anonymous letters laced with bacterial spores were dropped off at a U.S. postal office. Far too small to be seen by the naked eye, these spores made their way through the mail to media companies and congressional offices, infecting people and causing a devastating illness that you've probably heard of before: anthrax. On October 5th, the first victim of these letters died, and another 4 people died soon after.
The 2001 anthrax attacks were an act of bioterrorism, a deliberate release of harmful biological agents to cause illness or death. Biological agents are bacteria or viruses or toxins extracted from living things in the environment, and their deadliness depends on the agent, the amount of that agent, and how it gets into your body. Some, like Bacillus anthracis, the one that causes anthrax, are deadliest when they're inhaled. So, in a bioterrorism attack, they're dispensed in an aerosol spray or enclosed in something like a bomb or an envelope so that they're released into the air when it's opened. Other biological agents do the most damage when they're ingested. So, they're used to contaminate water and food. And others, like viruses, are introduced into a population of people with the intention for them to quickly spread from one person to another.
The exact reasoning behind the 2001 anthrax attack and the person or people responsible for it is not entirely clear. In 2008, the FBI concluded that a government scientist who they'd been surveilling for about a year before he took his own life was solely responsible for mailing the anthrax letters. But a few years later, a group of independent scientists assembled at the request of the FBI determined that although the science was consistent with that one person being the perpetrator, it didn't prove it.
We often frame science and scientific discoveries in a positive light, and for very good reason. I mean, science has given us vaccines, antibiotics, and other drugs and technologies that have allowed people to live for so much longer than they did in the past. But when science falls into the wrong hands, it can do a whole lot more harm than good. Welcome to Tiny Matters. I'm your host, Sam Jones, and I'm joined by my co-host, Deboki Chakravarti.
Today on the show, we're talking about bioterrorism, the science behind why certain biological agents do so much harm, and how they've been used over the course of history. And we'll hear from a scientist who's working to develop drugs to save people who've been exposed to them.
But before we fully dive into biological weapons, I think it's important to define a few things. Although chemical and biological agents are often grouped together in the context of bioterrorism, they are technically different. Things like mustard or sarin gas are well-known examples of chemical agents, and they typically make you sick right away. Biological agents are often more of a slow burn. There's a lot to say about chemical weapons, their regulation, and their use over the course of history. But in today's episode, we're focusing on biological weapons.
The 2001 anthrax attacks were scary, but not totally unexpected and certainly not unprecedented. Humans have been weaponizing microorganisms since well before we understood what they were or what made them deadly. It wasn't until the mid to late 1800s that scientists came to the consensus that microorganisms could cause disease. This new knowledge, called germ theory, was a major turning point for medicine. It allowed scientists to more effectively treat and prevent diseases. At the same time, it created an opportunity for people who wanted to use those germs as weapons.
But biological warfare goes back thousands of years, and there's a whole lot that we could talk about, like arrows and other weapons being covered in things like animal blood, snake venom, and the saliva of rabid dogs. But for this episode, we're going to stick with some of the events that really stood out to the researchers we spoke with. One of the most notorious stories was the Siege of Kaffa in 1346. Kaffa was a walled city located in what's now Crimea. Soldiers from the Mongol Empire reportedly catapulted the cadavers of bubonic plague victims into Kaffa. Catapulting cadavers is already a really morbid idea, but the real goal here was to make their enemies inside Kaffa sick. A little background on the bubonic plague, which is often referred to as the Black Death. It's caused by the bacterium Yersinia pestis and carried by rats and fleas. Today, it can be treated with antibiotics. But back in the 1300s, something like 50% of people infected with it are believed to have died, and that amounted to tens of millions of deaths.
At the time of the siege, Kaffa was an Italian center of trade, so there's speculation that this biological attack spread the Black Death throughout the city, infecting Italian soldiers who then left on ships along with infested rats and fleas that tagged along, taking the disease with them as they traveled through Europe. However, the direct connection between the catapulting of cadavers and the spread of the Black Death throughout Europe is highly controversial, and many researchers are doubtful that it was the sole cause of the epidemic spread. Still, catapulting diseased cadavers at the enemy was not restricted to the 1300s. For many centuries after, this was a shockingly common tactic.
Now, let's fast forward to the 1700s and the well-documented weaponization of the viruses that cause smallpox. Smallpox is highly contagious, and it causes extreme blistering, scarring, blindness, and back then, typically death. Smallpox made it to the Americas by way of European colonizers, who used this strategy a lot to kill native peoples. British captains would take blankets from their smallpox hospitals and gift them to native people. One captain even noted in his journal, "I hope it will have the desired effect." And there are a whole lot of other journal entries by other military officials that are very similar. It's absolute pure evil.
And these horrific stories are all from the era before germ theory, before people had a general understanding of microbiology. Unfortunately, the knowledge of what microbes are and how they make people sick opened up the door to more awful stories as people figured out how to mass produce these microbes or their toxins to do the most damage possible. There's evidence that during World War I, some countries developed secret biological warfare programs, doing things like trying to find ways to contaminate animal feed with the bacterium that causes anthrax so that the meat would infect whoever ate it. But it was between World War I and World War II that one of the most notorious biological weapons programs began.
In 1932, the Japanese government created Unit 731, officially called the Army Epidemic Prevention Research Laboratory, where thousands of Chinese and Korean prisoners were subjected to horrific experimentation. These prisoners were infected with microorganisms, including ones that caused cholera, smallpox, botulism, bubonic plague, and anthrax, and they were left to die as researchers studied the effects. This is unfortunately far from the first or last example of experimentation by people on people in the name of science. And it wasn't long until the Japanese army started scaling up, dropping bombs with plague-infested fleas or food or clothing into China, hoping that it would spread disease. It's not clear how many people were killed by these attacks, but some historians have estimated the number is in the hundreds of thousands. This is all really, really dark, and it only gets darker. At the end of World War II, the U.S. government granted the leaders of Unit 731 immunity against prosecution for their war crimes if they would share the data from their experiments.
In the United States, what's considered the first bioterrorism attack was executed by the Rajneesh cult in 1984 in Oregon.
So, if you have seen the Netflix docuseries Wild Wild Country, it is about this cult, and I personally thought it was really well done. Okay, sorry to Bookie. Please keep going. I just wanted to point that out for people who might want to go on a cult deep dive after they listen to this episode.
The cult had taken over a large area of land and they were at odds with the government. Local elections were coming up and they wanted to stop as many non-cult voters from participating as possible.
They wanted to control the political offices in the city, the mayor, the city council, whatever those offices were. And they decided the best way to do that was to get people sick with salmonella so they wouldn't vote because they'd be sick. So then they went around and sprayed it on salad bar items, and a lot of people got sick.
That's Marie Chevrier, a public policy professor at Rutgers University, Camden. Ultimately, the leader of the cult admitted the cult's guilt when he blamed a defector. If he hadn't, the cult would probably have gotten away with it. At that point, the CDC had concluded their investigation of the outbreak and reported it was natural. That's the thing about many biological weapons, including salmonella bacteria.
One of the advantages is that they're relatively easy to disguise as a natural phenomenon.
The Rajneesh cult triggered a reported 751 cases of food poisoning, 45 of which required hospitalization. But the CDC estimates that every year in the United States, salmonella bacteria cause over 1 million infections, over 26,000 hospitalizations, and around 420 deaths. It just becomes really hard to separate what's bioterrorism from what's just an unfortunate thing that happened because, the world's full of microbes and sometimes they just, they contaminate our stuff. So what was considered the first bioterrorist attack on US soil almost went completely unnoticed.
We hope it's clear by now that biological weapons are serious business. They've done and could do a lot of harm. But there are scientists out there trying to understand them to keep people safe. Let's talk about that.
Please, let's learn more about some good things.
We'll start by going back to the biological agent we kicked things off with, Bacillus anthracis. I promise we'll get to the uplifting stuff soon, but first, let's get into a bit of the nitty-gritty.
There are several reasons why anthrax is such a dangerous disease. So, number one, it's a spore-forming bacterium.
That's Elizabeth Ambrose, a chemist in the Department of Medicinal Chemistry at the University of Minnesota. Remember that spores were what were in those letters during the 2001 anthrax attack. They're essentially really tough, dormant forms of the bacteria.
They can actually remain viable in a variety of really inhospitable environments. So, they can last for hundreds of years in soil, in wool, things like that. And also the spores can be very easily inhaled.
And you might recall that inhalation anthrax is the most deadly.
Inhalational anthrax is worse because when you inhale the spores, they basically set up shop in the alveoli of the lungs, and they're very comfortable there. And they immediately germinate, and then you start getting bacterial colonization there.
Alveoli are tiny, balloon-shaped air sacs in your lungs where oxygen and carbon dioxide are exchanged, keeping oxygen flowing throughout your blood. As anthrax-causing bacteria spread, they produce a toxin. That toxin's made up of 3 proteins. The first is the protective antigen, which creates a little hole in the target cell, allowing the 2 other toxin proteins, the lethal factor and the edema factor, to enter.
So the edema factor does what its name implies. It causes swelling of the extremities, just basically makes life very miserable for the person who's infected. The lethal factor is responsible for the severe toxicity that's involved with anthrax infections.
Let's talk about the lethal factor. It's an enzyme, and an enzyme is a protein that generally speeds up chemical reactions. In the case of the lethal factor enzyme, it does a bunch of things once it gets into your body, including chopping off the ends of proteins called mitogen-activated protein kinases, which is a real mouthful, so we're just going to call them MAPKKs. MAPKKs are really important for our immune system. They help our bodies recognize, target, and break down invaders, like, say, the bacteria that causes anthrax. The lethal factor stops the MAPKKs from doing their job, which means they can't protect you from developing anthrax.
It also operates by other pathways that result in disruption of endothelial cells. So, for example, cells that line blood vessels, that line lymph vessels, basically leads to leakage of fluids from those vessels, so circulatory shock and death of the host.
So that is all very scary. But the good news is that there are a couple of vaccines available to prevent anthrax. There's one that messes with the protective antigen, that toxin protein that helps the other bad proteins get into our cells.
And there's another vaccine, which is probably the most widely used vaccine. It's been around for a while. It's called Biothrax. And so that's the vaccine that the military gets. It requires multiple doses over a number of months. Those of us who work with anthrax, we also get that vaccine as a preventive measure.
Once someone's been exposed to the bacterium that causes anthrax, their options are limited. There are antibody therapies stored in the US's Strategic National Stockpile, which is the country's largest supply of life-saving medical countermeasures for different diseases. But these antibodies are most effective if they're used alongside antibiotics. The antibodies block the toxin, while the antibiotics kill the bacteria making the toxin.
But there's a catch, and that is that you have to get to the infected host very, very quickly because toxin secretion happens immediately. This is another reason why inhalational anthrax is so much worse. And the symptoms of anthrax infection, at least in early stages of the disease, are very nonspecific. So could look like flu-like symptoms, could look like a bit of a cold. And then after a few days, in some cases, the disease just hits like a ton of bricks. And at that point in time, it might, in fact, be too late to get rid of the toxin because there's huge amounts of toxin that are circulating in the system. Even if you administer antibiotics at that time, there's often enough toxin left to cause fatal residual toxemia. You know, the main objective is to be able to inactivate the toxin. If you can do that, you're going to really reduce the threat of anthrax as a disease.
So, antibiotics plus antibodies is a great combination because with just the antibiotics, there could be so much toxin left that it's still fatal. But how feasible is getting antibiotics plus antibodies in enough time to save someone's life? Aside from antibodies not being immediately available at a pharmacy or another easy-to-get spot, they're expensive to produce and trickier to store than most drugs. It'd probably be a little comforting to know there's a drug that you could just easily get if you were exposed to anthrax. That's what Elizabeth and her lab are after.
Our objective is to develop an easily distributable, effective, and drug-like small molecule therapeutic to be used as an anthrax antitoxin. So something that's actually going to stop the work of that lethal factor enzyme in its tracks. And if we can do that, we will be pretty much eliminating the threat of anthrax as a disease.
But that's a challenge because the lethal factor itself is difficult to treat, in part because it's a type of enzyme called a zinc metalloenzyme. The thing you really need to know about zinc metalloenzymes is that they are everywhere.
I mean, zinc metalloenzymes play a role in multiple biochemical processes that are essential for health. And, you know, if you interfere with those, again, you could be causing more problems than you're solving.
Because zinc metalloenzymes are found all throughout our bodies, you can't just block all of them to destroy the lethal factor. It could cause a lot of damage. So, right now, Elizabeth and her lab are finding ways to specifically target the lethal enzyme without hitting all those other zinc metalloenzymes that we need to survive.
Okay, so before we wrap things up, I want to go on a bit of a tangent.
Okay, I'm listening. I'm here.
So I want to talk about a biological agent, of course, but one that people willingly inject into their faces.
I see. I see where you're going with this.
Botox.
Yes.
So most scientists would say that the most toxic substance known to humankind is botulinum toxin, a protein made by the bacterium Clostridium botulinum. It causes a disease called botulism. You usually hear about botulism in the context of canned goods.
So that's why they say you're never supposed to buy a can of food that's dented or looks warped in any kind of way, right?
Yeah, so any damage to a can that could create even a tiny opening might allow Clostridium botulinum bacteria in. And because it's a bacteria that thrives in low oxygen environments, it can really rapidly grow and produce botulinum toxin. This toxin is so dangerous because it blocks your neurons from releasing a signaling molecule called acetylcholine. Without that signaling, your muscles can't move. You're paralyzed. The first symptoms of botulism often show up in someone's face as muscles that control their eyes and mouth begin to weaken. That paralysis spreads further down their body, eventually damaging muscles they need to breathe. Without immediate medical attention and the antitoxin, which does exist, thank goodness, botulinum toxin will kill you. Because it's so lethal, botulinum toxin has been a major biological warfare concern for over a century, and apparently a lot of countries tried to weaponize it during multiple wars. But there's no proof that anyone was actually successful. Botulinum toxin has had a lot of success in another arena, though, the beauty industry. Botox is a dilute solution of botulinum toxin, and it's injected directly into facial muscles, dramatically decreasing their movement, which leads to fewer lines and wrinkles that would normally form from that movement. Although the history surrounding exactly how Botox came to be is contested, botulinum toxin is believed to have first been used in a clinical setting in the early 1970s as a treatment for strabismus, which is a condition that makes someone cross-eyed. So the Botox weakens the muscles around the eyes, making the patient less cross-eyed. In the late 1980s, an ophthalmologist was using botulinum toxin to treat a patient for a different facial disorder, and they discovered that the patient had fewer wrinkles around their eyes following the treatment. The ophthalmologist then injected the face wrinkles of her receptionist, and that was the first time botulinum toxin was used for aesthetic purposes. Now, Botox is an enterprise worth almost $3 billion, and it's prescribed for a range of conditions, from migraines and preventing an abnormal heartbeat during open heart surgery to treating cold hands.
I have so many questions about what the receptionist was feeling when this ophthalmologist was like, "Hey, you want some experimental treatment for your
I know.
wrinkles?" Like, are you flattered, excited, insulted? Like, what is the process there?
Totally.
That's technically not in the purview of our science that we're interested in. But I do appreciate the tangent. It feels very fitting that in an episode about how we as humans have managed to turn medical knowledge into something scary, that we have also hit on how sometimes learning about scary things has contributed to medicine.
Thank you for giving my tangent a bit more purpose.
No worries. I'm always here to validate a tangent. But we should probably get back to bioterrorism and wrap things up. There have been many international treaties concerned with biological agents over the last century, particularly after the First World War. In 1925, the Geneva Protocol prohibited the use of biological weapons. And in 1975, the Biological Weapons Convention went even further and banned the development, production, stockpiling, and acquisition of microbial or other biological agents or toxins. Treaties are great if people agree to sign them and follow them, but that's just not always the case. And that, along with humanity's long history of biowarfare, continues to keep people on edge, including all of the researchers that we spoke with.
9/11 and the subsequent anthrax attacks really, I think, brought it home that, we need people to be working on these countermeasures. One tends to think, and I think this is only natural being human, that if there hasn't been an attack in a while, that means that it's really not of all that high concern. But the threat of a biological warfare agent has not decreased. And we are still not very well prepared to handle a broad-based attack, especially on a large metropolitan center.
There are differing opinions out there on the likelihood of a biological attack, but something people do seem to agree on is the importance of ongoing research to develop antidotes and treatments so that, in the unfortunate case that there is an attack, we're all prepared.
Thanks for tuning in to this week's episode of Tiny Matters, a production of the American Chemical Society. I'm your executive producer and host, and I am joined by my co-host, Deboki Chakravarti.
This week's script was written by Sam, edited by me and by Ruben Rodriguez Perez, and fact-checked by Michelle Boucher. The Tiny Matters theme and episode sound design are by Michael Simonelli, and our artwork was created by Derek Bressler. Thanks to Elizabeth Ambrose, Marie Chevrier, and Vincent Barra for chatting with us. Although you didn't hear from Vincent, who's a medical historian at the University of Lausanne in Switzerland, he was incredibly helpful as a consultant for this episode and provided a lot of great information on the history of biological warfare. So thank you, Vincent.
If you haven't rated and reviewed us on Apple Podcasts, Spotify, Stitcher, Audible, or wherever else you listen, please do. That's how people learn about us. That's how we are able to get on the charts, so we would really appreciate it. And if there are some tiny things that you think matter and that you'd love us to explore in an episode, please shoot us an email. That's tinymatters@acs.org.
We'll see you next time.